Hello, how are you? I unfortunately had to cancel our normal class because I had a clausura. I will have to be available the whole Friday. And as an alternative, I have tried to offer this pre-recorded class that I will make available on Moodle, as I have explained it in the last email. And yeah, let's go. I hope it's not that worse than our normal classes. Of course, we lose a little bit of interaction, but on the other hand, I will be straight to the topic, and we can also exchange emails, and you can talk to me anytime you like about your doubts for the final projects that you're going to present in the next Friday. So, first of all, how are you? I would love to hear from your side as well. Unfortunately, I will not be able. Let's get back to our um, agenda. And I'm sharing my screen. This is, let me see. This is the course. We had only 2 classes left, as you have allowed me to have one more class that will be on the 3rd of February. And the last topic that I was going to show you that we are going to talk about was the topic of social network analysis. I also thought that if time allowed, I would give you a hint on how to use databases right from Python as a way to store data. So let's go. Let's start it. Social network analysis. This is a topic that was popularized by the rise of the social networks, but this is not contained in the social networks, in the online social networks world, but also something that allows us to explain and study communities and a type of data that organizes as edges and nodes. So for some kind of studies, this is much more efficient to represent data than other types of tabular data or textual data. We can represent and we can study communities using SNA techniques, and of course I will show you some packages in Python that allows us to explore this kind of data. So I have these topics here, graphs. I will talk a little bit about knowledge graphs, and we'll show you Python packages as NetworkX and perhaps some others. In terms of theory, I would recommend one book if you want to dive deeper into the theories behind network science and network analysis. This book from Barabasi, first of all, it's a free online book, and it's one of the Bibles in the field on network science. So if you read online, it introduces the graph theory, what are random networks, the scale-free property of some networks on the case of epidemics and many natural phenomenon that they organize as scale-free networks with preferential attachments, which is more or less like the saying that for those that already have, much more will be given. That's why we prefer to attach in these nodes where much nodes are already attached. This also sparked a lot of interest when the first search engines came, and when Google created an algorithm called what is the name of the algorithm? Well, let me think a bit. This is very good for classes which are recorded. And the algorithm is PageRank, and the PageRank algorithm was created to evaluate how important some web pages are. It is the main criteria used to evaluate the responses for your searches in search engines, much more than the times that the words in your query appear. The importance of the pages that you are looking for is measured by PageRank, and actually this algorithm, which was a product of a thesis from these two guys, Sergey Brin and Larry Page, that made Google become what it becomes as one of the most one of these giants in technology in the world. And PageRank assumes that a page is important based on how many pages are connected to this page. So if a page receives too much links, inbound links, it's important. And if a page with lots of importance points to another page, this page to which this important page points or links to is also important. And this is the algorithm, the main algorithm along many other algorithms that help us decide what is important, or help Google decides what pages are important in a web consultation. So we have this page in Wikipedia that explains the algorithm, and it can be modeled because the web in itself is a graph, is a graph where the pages are the nodes and the links are connections, are the edges. So if a page points to another page, these two pages are connected. One of the first or the most common examples when we study social network analysis is the Karate Club example. Let me see. Okay, the Karate Club is one. It's an anecdote about a karate club that had the teacher and the owner, and they have fought, and they mapped the interactions between the students and these two people, and you could predict if a person which was not in the list was connected or to one of the two subsequent clubs that appeared after the split, based on the connections, the friendship connections that they had before the split. So you could predict which ones would belong to each club. But also, there are other examples in which we can see the studies of network analysis. One of them happened in China in the beginning of the COVID. So with the surveillance, with the cellular mobile data, they could track which people were in contact with some other people, and then if one of the persons in this network become infected by COVID, the other ones would be contacted, because they keep track on these interactions, and you can create a kind of temporal, always dynamically change network using these connections over time. So if a person, you can create a connection that happened in a specific time, and the connections are being updated through time based on if whether people met each other or not. And in this book, Barabasi explains how to measure communities, what is a community of nodes, how nodes can organize into communities. Other phenomena like spread of viruses, the likeliness of one computer in the network to be attacked by others. Also, one very common example in the academy is the citation network. We measure our importance as researchers by the number of citations that we have in our papers by other colleagues, and if these colleagues are high in the academic ranks, their citations to our papers are even more important. So there's a lot of science besides it. So I would recommend this book for those that want to go deeper. It's well organized into chapters. So explains connectivity, lots of complex systems that can be studied using this framework for studying. And so after these first examples, it starts to lay out the graph theory. What is a network? What is a graph? Some measurements from graph, like degree of a node, the average degree of a graph, the degree distributions, how can we represent a graph into an adjacency matrix, some kinds of real networks, weighted networks, directed networks. So for example, if I have a relationship, family relationship network, it's a directed network because if I have a son, he or she is my son or daughter, but I am not her or his son or daughter. So it's a directed network because there is a kind of directionality in our connections. But if I say, for example, who knows whom in LinkedIn or in Facebook or in any other social network, if I know a person, this person knows me, or at least is connected to me. So this is a non-directed network that it can also be represented as a network. And the degrees of connectedness or the identification of communities is a very special topic because it helps in lots of ethnographic, sociological studies to understand what is the core of a community. If you work in marketing, where should you start to deliver the messages to acquire a faster response? If you work with epidemiology, where should you put your efforts to contain some disease? And most of you may have heard about the 6 or 7 degrees of separation theory that says that everyone in Earth is based on a knowledge network. Everyone is separated by the maximum of 7 steps in order to go to one person to another. Okay, this is the theory. Unfortunately, this is not a full course on network analysis. This is the material. I would love to know that you are interested and you could develop a little bit more in this theory, but this is a course regarding tools. And what I have to offer you today is a notebook that explains a little bit how to use Python to represent network science, network graphs. So this notebook is here, notebooks, Python tasks, and SNA graphs analysis. This is the first notebook I'm going to show you today. And the other notebook, if we have time, perhaps I will make this 2 different recordings, and then you can see if you may watch both at the same time or one at a time. And we are going to play with this Network X package. And Network X is a package to represent networks or graphs. So if you go to networkx.org, there's a nice there are nice material here to see that to start using. Basically, in the tutorial, it shows you how to create a graph. So import network X as NX, and you instantiate a graph. So this is a simple graph, nx.graph. You have G is a graph, and then once you have the object of a graph, you can create nodes. So add node. I'm adding a node that is called 1. I can add nodes from any container in Python, like a list, like a dictionary. I can add nodes with properties. So here I am adding nodes. I have a list of tuples, and every tuple has the name of the node and has some properties of these nodes. The properties doesn't need to be homogeneous among the nodes, but actually you expect them to be homogeneous, because in order to find out the properties of the nodes in a straightforward way, we would expect that all the nodes have some common properties. And there are lots of different ways to create nodes from existing data. Being lists the most easy. You can create nodes from data frames, from a column and a data frame. You just pass the column of the data frame as your list. I will show you in the code. And you can create nodes and you can create edges. So if add node, you just need to pass a list of nodes. Add edges expects lists of tuples, lists of pairs of nodes that will be connected. And then here in my predefined graph, I'm adding an edge between node 1 and node 2. And then you may ask, oh, what if node 1 and node 2 does not exist? Well, if you add an edge to a non-existing node, the node will come to life automatically. Very convenient. But yeah, it does not check if the node exists. If the node exists, it will take as it is. If does not, so in this case, it's like a dictionary. If you create if you change the value of a key in the dictionary, it works. But if you assign a new key to a dictionary, to a value, it creates the key in the dictionary. So add edges. I'm adding a new edge. I can unpack a list of tuples of edges like this. I add edges from here. I have a list with 2 tuples, so one edge, another edge. And I can also add edges from another graph. So here I have graph G, graph H, and I can add edges to G that exist in H. I can clear the nodes and the edges from the graph, and so on and so forth. So it's very, very straightforward. So if I say add nodes from, and I pass a string, as you may remember, is a container of characters. So it will create nodes S, P, A, and M. And I can create an edge between 3 and M. And okay. And I have lots of ways to examine the elements of a graph. I can list the g.nodes, g.edges. If I can even see more data than only the nodes, I will show you later. I can remove elements from the graph, so remove a node, list the new nodes. I can use the graph constructor, so add edge, and if I create an edge list, a list of tuples, I can use this list of tuples to create a new graph. And a dictionary as well can be used. And every node, the graph in itself, every node and every edge can have properties. I will show you in a second. But here I am creating a graph, passing so some edges, and I'm saying that all of these edges will have a color, and this color will be yellow. So color is a property to all the edges, and it will be yellow. It doesn't need to be like this. So, but actually, it's very simple to assign properties to every instance of our nodes. Okay, I can have attributes of the whole graph. I can have attributes for the node, and I can have attributes for the edge. Any question? You will not be able to tell me, but I may try to to guess some questions. What is the difference between nodes and edges? Well, nodes and edges. Edges connect nodes. Professor, we will never do this stupid question. Okay, I'm sorry. So let's go for a more likely question. I guess you have to write me. But I will give you all the elements. Adding attributes, I have told you before, I can add an attribute to a graph, to the whole graph. I can modify attributes of a graph. I can add attributes to a node, as I said before. So I just need to, when I create a node, I can pass a dictionary, or I can use this named property like add node 1, comma, and then I say something, some property and the value of the property that will be attached to the node. And likewise, I can have attributes to the edges. Next topic is the type of graph. As I said before, we can have directed graphs and non-directed graphs. A directed graph makes a difference between the direction from the relationship. So I can have two nodes which are connected like this and like this. So like I was saying before, relationship, family relationship patterns are more directed. Okay, if you're my brother, you are my brother. Yeah, this is, but if you are my mother, I am your son. So this is a different type of relationship. It's a directed graph. We have multi-graphs, so multiple edges between pairs of nodes. This can be used for a graph that evolves through time. And okay, this is in a nutshell. This is all you need to know in terms of the graph structure in itself. We can use graph operations, so subgraph, union of graphs, disjoint union, Cartesian products between nodes. You can operate in graphs using lots of specific methods. And the nice thing is that once you have built your graph, you can analyze your graph. And well, you create a graph and you can analyze. So what are all the connected components? What are the cliques? So I would say that if you refer to the connectedness chapter on this book, you will understand what are the measurements of connectedness between nodes. So 4 is considered to be one important node because it connects two subgraphs. If you cut the connections to the node 4, you will disconnect two separate networks. But if you disconnect one, only one will be disconnected. So there are lots of ways to find the connected components of a network, and there is the clustering coefficients that that captures the degree of connectedness. And you can measure lots of ways two or more nodes can be connected. So there's a lot of theory about this in multigraphs, undirected graphs, self loops, and so on. And we have subgraphs, and one of the tasks in social network analysis is to find cliques. Cliques is a complete graph inside the graph, so a complete subgraph inside the graph. It's so you are a class of students, but some of you are tightly connected because you know for some time, you go out together. So these are the cliques in a graph. So all of you know me, some of you know each other, and some of you are cliques of people, if we represent relationships, friendship relationships like this. And we can analyze, because we can analyze graphs that we build using NetworkX, because it gives us methods to identify the connectedness of graphs. We have also methods to draw graphs, although the graphs can be visualized if they are not that big. If you have big graphs, the visualizations are not as good as you may expect. And but it's very easy. You just have to import matplotlib, and you have networkx.draw. So when you draw a graph that you have built, you can have lots of different ways to display the information in your graph. You can choose the way you display. So there are some different things that can be taken in account. You can use the properties of the edges to make the nodes closer or more separated apart, and I will show you in our code. Yeah, so this is the library. If you it doesn't go too much into the specificities of the science behind, but it's more like a quick, very quick introduction on these topics on how to create graph, and then if you have here an analyzed graph, this is far from being comprehensive. But if you see the reference, linear algebra, relabeling, reading, drawing, randomness. Well, if you take the functions or the methods that are available to a graph object, you see that there are lots of functions. Is directed, is empty. If a subgraph of a graph that has some properties, density, you can, where's connected components? So this, or perhaps this is an algorithm. Yeah, communities, you can identify communities in a graph, top level communities. You can find the cores of a graph. You can take the distance measures from all node to another node. Link analysis. So we have to go a little bit deeper into the theory to know what kind of things make sense, how similar one node is from another, and so on. So we have these algorithms, and we have these functions. We talked a little bit about the graph types. The main difference are graph, undirected and directed graphs, multi-graphs, multi-directed graphs, and functions, algorithms, some ways to generate graphs. So we can generate graphs out of almost nothing, just passing some parameters. So these are types of graphs that can be generated right away. Some linear algebra operations that can be applied to graphs, like how to convert a graph into other representation, like a matrix. Every graph can be represented as a matrix of columns of nodes, rows of nodes, and so on. But there's a lot of theory. Let's go to a more practical part. And these are the references. Network X, Barabasi's book, and my code. Yeah, we have this notebook. And although the theory is not as deep as we should expect, let's see how to apply these to our digital humanities methods. And I will show you some examples on how we can study data that behaves like a graph. Well, I have a worksheet here. So notebooks, Python course, data. I guess it's here. Yeah, this was I could show you in a data frame. I could show in a data frame. Yeah, I just need to fix one thing. It's here on XLS. Let us run this Python graph libraries. Oh, PyDot's not here. So I have to install. Pip install PyDot. Okay. And now it works. Network X. I'm reading this file. And this file is just not found. XLSY data. Oh, yeah, I guess there's an additional data here. So if, or maybe another. No. With Excel, type methodology. Let me find out. I will pause. Yeah, I didn't read the error message. It's not just the path, but it says that Pandas requires version of Excel reader. So what we have to do is we have to install. No. Excel reader. Let me see if it's this right. Yeah. So I just need to install this other package. And apparently it will work, but not work. Okay. I need to say install -u to update the package. Now, okay. And I hope now it works. It does not. I'll have to restart my notebook. So kernel, restart kernel, and then I will run again. Now I have it. So I have a worksheet that was one of a representation of our group when I used to work in the Austrian Academy of Science. We have it's an ontology. We have groups of entities. An entity can be a group, organization, a person, topics. So this is the entity. This is the type of the entity. All of the entities are classes, and these are the superclasses. So we have groups, we have languages, we have topics, and okay, these are the information. I will create a graph out of it. This was we were trying to represent how people was connected by topics, by buildings. Let me put the heading 50, and then we have some more things here. we have locations, we have people, the places where they work, the topics they work with, and I will use this data to create a graph. So first of all, I define some, well, these are the names of the colors in Matplotlib. I'm just showing the names of the colors. And I will choose, so how many classes I have here. So these super classes: linguistics, location, topics, person. I will, I'm just choosing some of the names of colors to pass as a property on my graph. These are the colors I have. And I will attribute one color to each of my classes. So a topic of interest will be defined using cornflower blue. A project will be coral. A person will be cadet blue. An organization will be burley wood, and so on. Now I'm able to create my graph using colors. How I'm creating a graph? First of all, it's a directed graph, so I am instantiating a graph. So this is my directed graph. First, I'm adding nodes. So for index in dataframe.index, I am adding all the entities as a node. So my entities are here, and I'm adding this as a node. Okay, and I'm saying, okay, what is the color of this node? This node will be colored like using my column colors, because I have assigned a color to each node. Now I am adding edges for each class to a subclass. So g.add edges from. Then I'm zipping all the entity values to the superclass values in each of the entities are connected to one superclass. So I know that Don Corleone is a person, Peter Norton is a person, project is a thing, a knowledge graph is related to network analysis, Volan Benghazi is a location, and so on. So here I am creating nodes, I'm creating edges between class and subclass. Then I'm adding edges between things or people that are based near each other, so in the same building. And here I choose the colors, and I choose a property which is a color and a property which is a relation. A color and a relation. Then I'm adding edges to member of. Then I'm adding edges to topic of interest. So according to this structure, I have things which are connected by common traits, common features. And when I create a graph, you can examine, I am adding nodes and I'm adding edges to make as an example on how those things are connected together. Edges to topic of interest, color, and relation. These are the properties of these edges. And has project, I'm adding the edges from the data frame, the color, and the relation. Okay, so when I do this, well, colors is not defined because I need to run this and this and this and this. Now I could see, for example, what are my nodes? These are the nodes of my graph. And what are my edges? These are the edges of my graph. So the edges of my graph, I have group, which is a thing and has this property. Organization, which is an agent and has this properties. All the edges are represented in this list, and all the nodes are represented in this list. These are all the nodes from my graph. Okay. And as I have my G graph, G is the network X classes directed graph. G is a directed graph. I can use matplotlib to plot the graph. So I am creating the object figure. I choose one layout for my graph, so that there's a link here to types of layouts. And then here I am drawing all the edges first. I pass a graph, and I pass what are the configuration of my labels. So G is the graph. Pos is the position, and the position will follow a layout object. Then what are my edge labels? I'm getting the attributes from relation. So every edge has some attributes. And I say the labels of my edges when I print will come from the property relation. I have a positions, font size, color, and etc., transparency, bounding box. I am passing to a figure object, and rotate equals true. So here I am drawing the labels. And then I'm drawing the graph, all the graph with different properties. Where my node colors will come from, where my edge colors will come from, where my node list will come from, my edges will come from, node size. When I create this graph, it takes some time, but I will create something like this. One by one, I first created the graph object, which the nodes with the edges. I add properties for those nodes and edges. And here I have so some properties are colors, relationship, and I can say that what are the topics of interest? History, digital edition, social network analysis is part of network analysis. These two people are based near each other, Wolfgang Bengasse and James Heisenberg, and so on. This is kind of it's difficult when we have a big graph, and this is not big, and things are a little bit difficult to visualize. But the structure is there, and I just want to show you with this first project that we have different types of nodes, and they are differentiated by colors. Different types of edges. The edges have a property which is the type of relationship, and the type of node, and colors, and text. And we have used in few lines, we have transformed this information that was represented in a Excel file like this into a graph like this, and this would help lots of analysis that we could do if we were studying things like the Karate Club or any kind of setting where we have people, we have entities, we have relationships, and so on. So this is the first thing I would like to show. I'll give a pause for you to think. But the problem with the pauses is that when you are recording is that they are not pauses at all. I'm just pausing and starting, and all you see is a continuous stream of recording. There's another library that is more, how can I say? It's more aimed at the layout of graphs. So I'll just show you very quickly. this library is data shader. So you can import data shader, but you have to install it. So pip install data shader and HoloViews install -u. And data shader and HoloViews are libraries that are much more than libraries for plotting graphs, but they also help to plot other types of structures. And I will briefly show what we can do with these two libraries. And they are more recently issued. They were recently issued, so they are newer than NetworkX. And when you install them, there are lots of other packages that are installed along. But once you have them, let's see what they can do for us. Wow, lots of things being installed. Ooh. I will comment this to take this out of our code as soon as it finish installing. I could pause, yeah. And it has finished installed. Now I'm commenting. And now I would be able to import data shader, HoloViews. And with these libraries, you can plot things. I'm generating a new random graph. So it's a data frame in which I am sorting out which nodes are connected to other nodes. So first I am creating node, the name of node, and then every time you do this, there will be a new source and target because I'm randomly connecting these nodes. And I will now plot this random graph in a different way, using different layouts. This is the random layout of my nodes. This is the circular layout. This is the force-directed atlas layout. They are all ways to plot graphs based on how close or how connected or disconnected the nodes are. And we can also, so force atlas 2, and we can, if we have edges, we can choose the way the edges will be. This takes a while, depending on the type of, oh, what's happening here? Scikit-image. Okay. Again, I will not bother you and make you wait. And here we go. We have installed Scikit-image and the dependencies. So I'm commenting this cell. And now we are going to be able to plot. Not yet. I have to run everything again because, yes, because once you load the package, so I will run everything after interrupting the kernel, restarting the kernel, and running all cells until this one. So yeah, run rows all above selected cell, and then I will run this cell as well, and then you will be able to see some of the options on this package. But mainly, as I said, it can be used to create nice graph visualizations, but there's no change in the theory behind the graphs that we are building. And this takes a while to render the graphs because these are huge graphs with as you can see, we have created some 20,000 nodes. But yeah, let's make it. Once they are plotted, you can see the differences between the types of layouts, and you can also create figures to make the plots bigger or smaller depending on what you want. Stopping for waiting. It didn't take too much. So a circular layout with the nodes, a force directed layout, a circular layout. Then you can see the strength of the connections between the nodes. Force directed bundle. So it's kind of different because here I want to get insights from the graphs based on the visualization, but the graph engine from these packages is much better. We can also, well, I'm creating here a data frame, and then I'm using graph plots to show the nodes from these data frames. So this graph plot is another library, but yeah, this is just a curiosity. So you can change some parameters to create different plots using this library, but this is more like for plotting than from studying graphs. So it's here in the notebook for you to explore, but it's not that important. There's another example where you can create graphs with categories, and you can also create interactive graphs using those libraries. Layouts, force directed, random layout, force directed bundle, as before. But let's create graphs using my library of choice, which is NetworkX, because it's more prone or target to the study of the graph properties than instead of visualizing. So here we will use NetworkX with some functions to create a graph, to choose a layout for the graph, and to plot a graph. So these functions will shorten, will make it easier for us to create the graphs. Let me just wait for this to finish.